I would like to thank the organizers for inviting me here. It's a pleasure. It was a pleasure to go to Telecom, and hopefully it will still be a pleasure in a few years in Saclay. So today I'm going to talk about like joint work with a former postdoc, Kevin Scaman, and a PhD student, Adrien Hendricks. So a bit of context before I start. So if you all here today is because there's a lot of data to work on. And what I want to emphasize, although this is an industry day, okay, so those problems with data come up in many areas. It's not only multimedia advertising, so this comes for all industries. I think we have talks from people from the automotive industry, so there are a lot of problems beyond Google and Facebook, but also a lot of problems beyond industry. So most of the techniques that we developed can be applied to other sciences. It could be geology, climate science, biology, and so on. So I want to emphasize that really machine learning is really here to be used everywhere and not only to make money on the web. So why do we care so much about those data? This is to get some form of automated processing. So this has been around for the last like 30 years. But with the amount of data that we have now, it's becoming like even more important. So before I start, let me like mention something which I find either interesting or amusing or depressing, depending on the day, is we have seen a series of hypes. So I'm sure that the workshop 4 years ago was called Big Data. Is this correct? I'm sure it's correct. I checked. And so we have a series of hypes. We say big data, and now I think I see data science and AI and machine learning. And sometimes people also say deep learning. So clearly, there is some reason for the hype. And this will be the topic of my next slide. But I just want to emphasize the fact that let's be careful. Okay, so we are very far away from any form of AI. So I will never use anymore the word AI in my talk. Right, so why is there some hype? Because it starts to work pretty well. And here are 2 examples that I took from random places. So machine translation, now working like really well, so well that you can go to a country and rely on that to go around. Or computer vision, those are results from my colleagues at Inria. So now you can start to analyze images in a very nice way. So this is like classically attributed to like a combination of 3 factors, a lot of data to learn from. So for all of those problems, there was a lot of data to learn. So for translation, a lot of translated sentences, and for computer vision, a lot of annotated images. Of course, a lot of power to deal with those data sets, and of course, some progress. Okay, there is not only like big data and big computers. You need some scientists and engineers. So at the end, intelligence in quotes, and I really insist on the quotes, is a combination of those 4 aspects. So algorithms, data, computing power, and models. But there is no universal model. And I think in this workshop, you will see a lot of various applications to different places. Always a common theme, okay, but still like dedicated models. So today, I'm going to focus on what I know well, which is the algorithmic part of the problem. So let's get to the technical content. So we have, I'm going to consider the classical parametric supervised learning framework where I have n observations, xi, yi. You can think of xi as being an image, yi as being a label on that image. And I'm going to predict y given x through a prediction function, which I will call h of x and theta. X is the input, theta is the parameter. And I will always assume that d is the size of the parameter space. So there are 2 classical like types of prediction functions. The first one is like so-called linear functions, okay, where to build a feature vector, which I will call phi of x, and you predict in a linear way by linearly combining the components of phi of x. So this has been used a lot in many areas of industry, and it still is, in particular in advertising, where the phi of x here is essentially monitoring your browsing in the web. So here, n is the number of clients of those like ad companies, so typically close to billions. And D is the number of websites that they store. And so for every website and every of their client, then they put a 1 if the client has been there and a 0 otherwise. and then by combining all that, they get linearly, they get some predictions. So clearly now they go a bit beyond, but this is really the core of their methods. So here, a huge dimensional feature space, okay, 10 billion, and then a big linear model. So this is working still very well in many areas where there is like no particular like natural structure, natural being like 1D, 2D, 3D. But if you go to computer vision, this is not what is being used anymore, and you have the so-called neural networks, which are used to classify images. So here, dogs and cats, okay, in two labels. And for that, it's not a linear model anymore. It's a model typically based on neural networks. So here, I've simplified it a bit. So you start with data, and you take linear functions over there, take some nonlinearity sigma, and move on like that. Okay, so this is the classical neural network, which is really the state of the art for those kinds of problems. So in this talk, I will mostly focus on this one, okay, because this is the one where you can say like you can prove guarantees, and this is still widely used, in particular when the input space is very big. So I will mention several places where things can be extended, and sometimes where things cannot be extended, and this will be left also for future work. All right, so the way learning is done, very classical. You have, you're going to minimize with respect to your parameter theta, some objective function, which is the average over the training data of some loss, okay? Some regularizer. So to make things concrete, the loss can be either least squares, okay? So this is used quite a lot, or logistic regression. So if your output is -1 or 1, so this is a cost function which you're going to use. So this one is convex in H. Okay, and this will make our life easier. So typically, most losses that people use in practice are convex. The big assumption is whether H is linear or not. So if H is linear in theta, then you get an overall convex problem. If H is not linear in theta, for example, for neural networks, this is not good convex. All right, so this is the problem we want to solve. So, so the goal, so just a reminder, I'm not going to focus too much on it today. But we don't care so much about doing well on the training data, about doing well on the testing data. Okay, so this assumes that you have some link between test and train, and this is a source of a lot of nice work at the moment. So I'm going to focus only on this. I'm going to be a pure optimizer for the next 45 minutes. All right, so what learning is doing, maybe like 20 years ago, people would say, oh, learning is an optimization problem. Okay, I want to minimize something. Okay, so I turn to my colleagues in optimization and just ask for their best algorithms. So this has been working for reasonably well, but the problem is that learning is not any optimization problem. You have some specificities, and the big specificity is the fact that we have a finite sum. Okay, so this is not any objective function; it's a finite sum. So if we don't leverage this fact, we can be okay. So the goal. The first part of the talk is really to tackle this finite sum structure. Right, so that's been like very classically like two types of techniques to deal with those finite sums. So here I have a finite sum, g of theta. This is a training error on my data. So here an example of fi is the loss for a single pair of observations plus the regularizer. Okay, it can be anything. So this is not limited to machine learning. Okay, many problems in signal processing as well are being cast as minimizing a finite sum. So you have the first class of techniques. This is basically gradient descent. So you go down the negative gradient from type step t-1 to t. And so the good thing about that is if you don't need convexity to define it, but if you make some assumptions of convexity, then you can characterize the speed at which it's converging. So you converge to the global optimum. And if you're willing to put like some strong convexity, I don't want to go into the details, then this is typically exponentially convergent. So this is the time it takes to reach, this is the precision after time t. And you can see that this is exponential. And there is one number which is characterizing this convergence, which is called the condition number. Okay, essentially, this condition number tells you if locally your function, the level sets look like a ball or look like long ellipses. And when your level sets look like a ball, the steepest descent direction tends to direct you toward the global optimum, Whereas if ellipsoids, right, so this is, okay, thank you. Okay, so, yeah, so it's linearly convergent. So this is all nice. It can even be accelerated. Okay, this is a very nice way by Nesterov, where you replace condition number by square root of condition number. So just to give you an idea of how big the condition number is, typically in most problems in machine learning, this condition number is between root n and n being the number of observations. Okay, so if n is 1 billion, this is going to be a very hard problem. So the problems we need to solve in machine learning from a pure optimization perspective are pretty hard because condition number being 1 billion. Okay, so this is converging linearly or exponentially, but very slowly. Okay, so this first kappa is pretty big, and the big problem is that every iteration you have to look to compute the gradient of g, so hence the full gradient. So you have to go through the data at every iteration, and when n is 1 billion, it's kind of a problem. So the image to have, so this is a fake plot. Okay, you do a few, okay, a few, let's say, not too many steps which are very costly. So on the other side of the spectrum, there is like a SGD, so stochastic gradient descent, where you replace taking all gradients like this, but just a single gradient taken at random. So here this is SGD with sampling with replacement. And so by design, every iteration, the cost does not depend on the number of observations. It's independent of n. But this is a positive side, but the negative side that the rate of convergence now is much slower. Where you go from exponential to only 1/t. So this is what is classically used in practice. All right, so here the image you should have is something of that form, where you do a lot of iterations, and some of them will make you go down. Some of them will even make you go up. So the term descent is the worst possible term for this algorithm. It's not a descent algorithm. Okay, it typically goes down, but sometimes it goes up. Okay, so here in this fake plot, I made sure it was going up once in a while. Okay, but on average, you end up converging. All right, so now this is like the two sets of algorithms. So summarized in a simple plot. So okay, so this is also a fake plot. So you will see up to the last slide, you will see only fake plots. Okay, so first you do fake plots that you wish you have, and then you make sure that your data fits your fake plots. No, that's not true. You take data, and magically the fake plot appears to be correct. All right, so this is time in the x-axis, okay, and distance to optimum in the y-axis in a logarithmic scale. Okay, so if you see a line in the semi-log plot, this is just linear convergence, exponential convergence, and there's the classical like Bach gradient descent, where you see a line. Why you see a line? Because it's linear convergence. Okay, so this is what is supposed to happen, but you see some staircase because as soon you only make updates to your parameter vector when you see the whole data. So for a while, you just spend your time reading the data and make no changes to your parameter. So you do nothing for a while, make a big step, and then do nothing for a while and make a big step, and so on. Whereas for SGD, then as soon as you see the first observation, you start to make progress. Okay, and after a single pass, while gradient descent has done nothing, you already have made a lot of progress. Okay? But then, if you start to go on for more iterations, then the 1/t convergence rates, 1/t being the number of iterations, will start to be visible. And in the semi-log plot, this goes to log t, to a logarithmic decay, because this is very slow. Okay? So the goal of there is a line of work in the last 5 years trying to get the best of both worlds, start as fast as SGD, and then end up also going down like a line. One bonus will be even the line will be even steeper. Okay, so this is so the class of like fast gradient techniques I'm going to present now. Right? So this is now called variance reduction. So we started this with Nicolas Leroux and Mark Schmidt in 2012. And this has been picked up by several other authors. And I'm going to present the Saga version that I've worked on with Aaron Defazio and Simon Lacoste-Julien. So we start from the classical SGD iteration. Okay, just select every function. You select a function at random, compute the gradient, and do a step. But what we're going to add is add some memory of past gradients. So here I'm going to store every gradient. Whenever I compute a gradient for the function I, I'm going to store it. Okay. And if I have computed this gradient before, I will replace the previous value, the old value, by the new value. So this means that at every step of the algorithm, yit will be the stored value of gradient I that I have at time t. Okay, some are very old, and some are very new. And we're going to add some term to the gradient. And the idea of that term is that it has the correct expectation. So what does it mean? It means that I of t is random, so I of t is uniform at random. So if I take the expectation of this term, I get the average of all gradients, which I call the full gradient of the objective function. This is a non-deterministic, the deterministic gradient is obtained by taking the expectation of that. Okay, so what makes SGD slow is the fact that I have the correct expectation, but the variance is not going to 0. So I always have some variance. And this causes SGD to slow down. Yeah. So what we add also has a 0 expectation when I take expectations of I of t. Why? Because this does not depend on I of t, and this depends on I of t. And I take the expectation, I get exactly this. So the gradient has a correct expectation. I'm still unbiased. This means that I'm going to converge to the global optimum, but this will have a reduced variance. Okay, so there is reasons for which the variance will be reduced, and the beauty of it is that the rate at which the variance is reduced is exactly the rate at which theta t is converging to the global optimum. So at the end, by simply adding those few lines, you can get we see faster algorithms. So let's see what we get. So now if I want to reach some precision epsilon, this can be distance to optimum in any way you want to measure it. Kappa is my condition number. So think of kappa as being n for most problems. Then we have seen SGD. Okay, so SGD will converge with, will take that amount of time to reach precision epsilon. So you see independence with respect to n. So this is fast when n is very large. But you see this is 1 over epsilon. So this means that if epsilon is 10 to the minus 7, this will be very large. On the contrary, gradient descent, we replace this log of this 1 over epsilon by a log. So you replace like 10 to the 8 by just 8. So this is like much better dependence on the precision. So if you want to have a good estimator, precise estimate, then this is okay. But you lose with the appearance of the number of iterations, the number of observations. Why? Because at every iteration, you have to compute the full gradient, so you get this O of dn appearing. And what you can show with those variance reduced technique, with essentially the same computation cost as SGD, you can either remove the product n times kappa by the sum n plus kappa, so you get a factor of n if kappa is equal to n, or you make simply SGD linearly convergent. And so at the end, you get what we hoped for, which is like that fake plot, essentially what those results are showing. And whenever you apply those techniques, you can reproduce those plots very easily. But since they look the same, I'm not going to present them. Right, so this is the first aspect. And one thing what we like to do as optimizers or as statisticians is to derive both upper and lower bound on the running time of any algorithm. Okay, those are upper bound, lower bounds. Upper bounds is saying that to reach precision epsilon, I need at most that amount of time. But other colleagues like to say the opposite. If you want to solve a problem where I want to minimize a given convex function, which is a finite sum with a given condition number, the best you can hope for, if you only access gradients, is in fact replacing n plus kappa by this. Okay, so this is the best you can do. Okay, and it turns out that this can be achieved by the similar trick as Nesterov acceleration. So you add some momentum, and you can extend this running time to this running time, which is always less. A similar order is kappa is smaller than n, but much better if kappa is bigger than n. Okay, so now, for this class of technique, if I want to minimize a convex finite sum, I cannot do better than this. Of course, this is only up to constants, of course. There's always like a lot of research trying to make those algorithms more robust and so on. But the overall time it takes is now we call optimal. So again, whenever you say the word optimal, you have to be careful on what it means. This is among all techniques accessing gradients one by one. This is the best you can do. All right, so this was for single machine optimization, and is now well covered for the convex case. Clearly, there's still open problems for the non-convex situations. This is a topic for another talk, but at least for the convex case, this is well studied, and the best you can do is something of that. All right. Now let's look at distributed optimization. So now I'm going to consider another finite sum, but the finite sum will be different. In the previous slides, every element of the sum was the loss for a single observation. Okay? So sometimes a small mini batch, okay, in practice. But now I'm going to consider a situation where I have like several computers or several processors, and now every element of the sum is much bigger. It's a data set, okay? And for example, it could be something of that form. I have like n data centers, and each of them is having some data set. The data set number I will have mi observations, and itself it's a finite sum, okay, because it averages losses over its own observations. Okay, so throughout the talk, we're going to assume mi is constant over every data center. It makes my life easier. And what we're going to study is is an ideal model of parallel processing where we assume that every function is sitting on a graph. Okay, so here there are nine nodes in the graph, and the functions are only allowed to exchange information with their neighbors. Okay, so 6 is allowed to send messages to 9, 4, and 5, but not directly to 1. Okay? So this is one way to model the fact that if you are in a network, whether like with big data centers, if you are across the world, you can only access data centers which are close by. This could be like if you have like a fleet of cars, you can connect to the neighboring cars. If you have a fleet of mobile phones, you can connect to your neighbors as a mobile phone. Or even in a parallel processing environment, you may access directly. So some nodes have a bigger bandwidth. Okay, so you may favor a node with a higher bandwidth. So why do you want to do that? As I've mentioned, this can be either because you have data sets in multiple places. So this work was started with a collaboration with Microsoft, and they had indeed issues between like data centers in the West Coast and data centers in Asia. And they wanted to have something where they could avoid communicating too much. But this could be multiple machines in the same data center. Okay, you may imagine that those machines are organized in different like blocks, so you may have a network also there. Right. So why what does it make the problem nicer? Is because you have now not only time constraints. So what I presented earlier on was just about time. What is the time I need to get to precision epsilon? Okay. But now I have time, but also communication time, number of communications, and this is important because I don't have infinite bandwidth. Or I may have some legal constraints. Okay, so for example, people now call it federated learning, which is exactly the same problem. You may have two limits on what you can exchange among computers. Okay, and this is one classical application areas. So now the goal is not only to minimize running time; it's also to minimize so running time would be the computation costs. I'm going to compute gradients of functions. So this is the same thing as before, but now I'm going to minimize communication time. Right, so this is the goal of the rest of the talk. So first, when you see like parallel processing, there's always a super simple way of making things parallel. This is, by the way, the one which is used a lot in industry. So why not simply take my classical deterministic problem algorithm, for example, Nesterov accelerated gradient, which is known to be optimal when I optimize functions. Okay, I can just ignore the fact that I have a finite sum over a network. Why don't I just compute, okay, and try to mimic and be formally equivalent to this algorithm? So as we have seen earlier on, the time it takes to reach precision epsilon will be logarithmic in epsilon, because this is exponentially convergent, but this will depend on square root of condition number. But for that, if I want to mimic this algorithm, so exactly be equivalent, at every time step, okay, I have my network, okay, and I have to make sure that some node is computing the average of all gradients, okay, because I need this to do the full gradient descent, because I need to distribute the computations of my gradient. So what is the problem here is I have a problem where, okay, sorry, every node has a gradient, okay, and has to share it with the other nodes in the network. And at the end, they want to reach a situation where all of them have the average of all other values. Okay, so this is, whenever you want to do like optimization on the network, you will always get down to this simple problem: how do I compute averages over a network? Okay, so this is another problem we have to tackle: how to compute averages over a network. Okay, so let me step back a bit for a very simple problem. I have n observations, xi1 to xin. Imagine xi1, xin are gradients, which I want to average. Here, I'm going to take them as being real valued to make my life easier. Otherwise, I will need to use matrices. It is going to be ugly. But imagine this is not in R, but in RD. And I want to compute their sum. Okay, the average like this. So first, it's well known that the average, the empirical mean, is equivalent to minimizing the square deviation to every element. So in a sense, computing the average is the simplest possible problem, minimizing the finite sum, which is simply like square functions. Okay, so the goal now is to compute such a finite sum. So you have two types of algorithms when you do parallel processing in that context. The first are called centralized algorithms. So those are algorithms where one node is allowed to say, I'm the boss, and I'm going to tell people what to do. Okay, and so here we can say 4 is the boss, okay, and then 4 is going to say, oh, let's first build a spanning tree over my graph. So I'm going to remove some edges to get a spanning tree. So if you do so, it is a classical result in computer science showing that the diameter of the graph of the tree that you obtain is at least twice the original diameter. Okay, so I'm going to do this. And now, whenever the boss number 4 wants to compute gradients, so 4 will have the value of the parameter vector. First, it will send the value to each of the nodes by following the spanning tree. Okay, so this can be done with a number of time steps, which is the diameter of the graph. Why? Because to reach number 7, you need to do 3 steps. Okay, and you can easily see that at the end, the diameter of the graph will be an upper bound on the number of steps you need to reach from any member of the graph to reach any node. And then once everybody has received the value of the parameter vector, then they can send back the gradients, okay, other direction. And while they send back the gradients, okay, the gradients are being averaged. And number 4 at the end has the exact gradient, okay, at the point that he had sent earlier on. Okay, so this at the end, the number of communication steps is proportional to the diameter, okay? And so here, when I made the time it takes, okay? So when 4 is sending things, the message is being sent to 3, 2, and 6 simultaneously. So they count as only 1 unit of time. So here, this is communication time, not steps. So if you define step as time, this is equivalent. So there is some parallel processing. When 4 is sending messages, so to 3, 2, and 6, this is done at the same time. So the overall time is proportional to the diameter. One important aspect is that there is no error being made. Okay, so at the end, you send the exact parameter vector, and you receive the exact average gradient. So at the end, when you apply this, your algorithm ends up being formally equivalent to plain gradient descent. And what we have shown with so my colleagues Kevin Scammon, Sébastien Bubec, Yin Tatli, and Laurent Massoulier is that this is the best you can do. Okay? So the dumbest algorithm you can think of just take the star of acceleration and distribute it in a very simple way, is in fact optimal. In terms of gradient steps, this we knew it because this is the best you can do when you have a single function. But in terms of communication steps, so you have two quantities which are entering the running time. You have the difficulty of the optimization problem, okay, condition number, regardless of the network, and the size of the network. So of course, if your data are distributed among like many nodes, okay, which are very far away, this is going to cost you more time, and this is well taken into account by both those lower and upper bounds. All right, so this is like so nice to have like lower bounds of complexity, but the problem is that those algorithms are not really robust. So why is this not robust? It's not robust to many things. First, if one node decides to stop, okay, so with 9 computers, the likelihood that the one node goes down is limited. But if you work with 10,000 computers, like they do in physics, for example, it's at every simulation, at least a few computers are going down. Okay, so this means that if 6 goes down, because 6 is close to the boss, then all of the other nodes which depend on 6 to send information to 4 will be lost. So one failure can be can be quite a problem because it can cut the network at a bad place. So when you cut a spanning tree, you always get disconnected components. Similarly, the graph may change. Okay, so sometimes the bandwidth is moving, so you may want to adapt to it. So in this area of parallel processing, people are not super happy about these centralized algorithms. At least this is what they tell me. And we're going to look at a different version, which is decentralized. There is no boss. Okay, everybody is happy to discuss with anybody, and this is called gossip. And this dates back from Boyd and even before. So the way it's going to work, it's also by sending messages, but it's going to be locally. Okay, so the way gossip is working, you have a node, 4, so 4 is not anymore the boss. So whenever 4 needs some information, it will ask its neighbors, 2, 3, 6, for their current values and average them. Okay, so 4 will do that, 5 we can do that as well, and 7 and so on. So at the end, at every time you need to update, you update the value at 4, you replace, let's say, theta I being 4, by the average of neighboring nodes. So you end up with what we call a gossip matrix W, which is essentially 0 if you're not a neighbor, and can be any positive number if you are a neighbor. Okay, so this is the way you exchange information. And in full generality, this can be done asynchronously, so nodes can wake up whenever they want. I'm going to deal with this later in the talk. But to make things simple, I'm going to study only the synchronous gossip, okay, where every node does it at the same time. So this means that at every time step, when I say do communications, all nodes will wake up and ask their neighbors. Okay, so at the end, every time you do a communication step, you're going to replace your current vector of estimates by W times this same vector. Okay, so here the gossip matrix W is here to model the fact that you have you're replacing your value theta I by an average of your neighbors. Okay? So why is it so nice and why it has led to a lot of nice work in optimization and control is because it's very simple. Okay? So the model that you have is simply a linear iteration. You go from step t-1 to t by just multiplying by a matrix. So this is all nice. Then, okay, so you can really check that if you apply these t times, you get the power t of the matrix times the initial vector. And since we initialize with the values we want to average, what we need to understand when you do gossip is a matrix power of a matrix. Okay, so this is something which is very simple to analyze. And so here, to make my life easier, I'm going to assume W is symmetric, W is stochastic. So it has to sum to 1 so that you really get averages. Okay, so this is make sure that if you send a constant vector, it remains constant. And positivity is also classical. Symmetry is to make my life easier. All right, so this is the gossip. So now we can do a bit of math. So since your symmetry W stochastic, your eigenvalues are between -1 and 1, Then you have a so-called eigengap between the largest eigenvalue and the second largest eigenvalue. And since you're doubly stochastic, the largest eigenvalue is 1. So the eigengap is simply 1 minus the second eigenvalue. And if you take the inverse of that, it's called the mixing time of the graph. So what does it mean to have a mixing time? This is the time it takes so that if you start from any place and you send information randomly following the edges, then this is the time it takes to reach essentially any other node. Okay, so the mixing time will tell you how big the graph is if I do like randomized computation on the graph. So it's different from the diameter. Why? Because diameter, you need synchronized communication, whereas here, you just like tell your neighbors, okay? So you gossip, okay? And then at one point, the gossip will reach any place in the graph. Okay? So this is, well. So since you have like a linear iteration, in a very similar way to convex optimization, you get linear convergence. So it converges exponentially fast to the global optimum. And the condition number now is essentially the eigengap here. So the time it takes to reach epsilon is the condition number for this problem, which is the mixing time 1 over gamma times log of 1 over epsilon. Okay, so this is the way it works. To make things concrete, I'm going to show an example. Okay, so this is like, imagine you have a node, you have 100 nodes that you have, it's not working, no. Oh yeah, it's not working. So you have, so you start with this, you have 100 nodes, which are in a two-dimensional grid, so every square is one node, okay? So you're connected to your neighbors in the grid, okay? So that node is allowed to communicate with that node, and this node. And we start with values which are of that form. So it's a big positive blob in the upper left and a big negative blob in the lower right. So doing averaging is getting to a situation where all nodes have the average of the network. So here it's 0, okay? So it should be like it has converged once it has reached like a 0 value. So I'm showing the video because it's very slow. Okay, so let's launch it. Okay, so T is the number of iterations. As you can see, it takes a while for information to go through the graph. Okay, so here I'm going to stop at 100 iterations, and once I reach this, I'm still very far away from seeing a converged value. So this means that when I do gossiping over a graph, because I'm not synchronized, I'm going to waste a lot of time having information spreading around everywhere. Okay, so to go from the lower right to the upper left, although you have like only 20 steps, okay, if you follow the shortest path, it may take quite a while for convergence. So this means that when you do optimization with gossip, you have to be careful that gossiping is very slow. So what I will show later on in the talk is some accelerated version where this is going to be much faster. All right, so now let's try to mix this gossip with optimization. So we are not the first one really to look at that. Many people have looked at this in the past, and some of them at Telecom. And this started with Nedich and Ostaglar like 10 years ago, and it is a sequence of paper trying to mix those ideas together. So I can't describe all of them, but they are a very nice set of papers. All right, so what we have done in this area, so with Kevin Scammer and colleagues, is first trying to characterize what was the best we could do. Okay, so again, whenever you attack a problem as an optimizer, you have the optimistic people that will try to provide algorithms, and the pessimistic ones that will try to provide like results of impossibility. So I've allowed my colleagues to start with impossibility results, and they provided some lower bounds. So if you want to optimize a function which is on the network, and you use some form of gossip, the best you can do is clearly you have to, the number of guidance steps has to be this, because this is what you would get with a single machine, so condition number, only dependent on the hardness of the problem. And in terms of communications, you have a product of difficulty of the optimization problem and difficulty of the graph, so the mixing time. So this is like a lower bound. So we knew that we couldn't do more than that. And if you look very carefully, I'm not going to do it. If you apply plain gossip, because gossip takes forever to converge at every iteration, then you're not going to achieve something of that kind. Okay, so essentially you would get 1 over gamma instead of 1 over square root of gamma. So this means that if you do the stupidest thing that we could think of, which worked in the centralized setup, it does not work anymore. Okay, if you're just trying to mimic the full gradient algorithm by distributing gradients, this is going to be too costly because gossip is too slow. So gossip is too slow. Now the question is, can we still do it by gossip? Okay? So this is what we're going to try to do. And for this, we're going to follow like a dual approach, and we're going to enter the convex world a lot. So what I've presented before, like in terms of SGD, we didn't need convexity to define the algorithm. Okay, it was just go down the negative gradient. We just need convexity to make sure it does converge to the global optimum. Okay, so and you can show that it also does work sometimes in a non-convex world. But now I'm going to use convex duality. So this means that I have no choice but being convex now. So I'm going to, this will be the mathy part of the talk. So I'm going to use some dual reformulation, which is due to Jakovetic and probably by people earlier. So this is my finite sum. I've removed the 1 over n to make my life simpler. So now every fi is my local function, which is on a node on a network. And the way you're going to formalize it is by assigning a different copy of the parameter vector to every node. So I'm calling theta I a local copy of the parameter vector, which is at node I. So clearly, if I just minimize this, every theta I will be the minimizer of fi, and I will not reach consensus. So often this problem of minimizing a sum is called consensus. And if I don't listen to others, I get to my own nice solutions, but I have not reached consensus. So the way to achieve it is to add some constraint that all of those local copies are equal. Okay, so this is a notation for I is a neighbor of j in the graph. So if your graph is connected, then having equality over all edges is equivalent to it to be to all theta i's to be equal. So here, this is just a reformulation. Okay, I'm just assigning different values, making sure they are equal. But now, what do I have? I have some constrained optimization problem. Okay, where I have now a simple objective, totally decoupled, and some constraints. So now I can use Lagrange duality, and which is adapted to those situations. So let's do the Lagrange duality. So I'm going to assign some Lagrange multipliers to my constraints. Okay, so one Lagrange multiplier vector for every edge in the graph. So I'm adding. So this is the Lagrangian of the problem. And now I can invert min-max. Okay, I'm not going to do the math, but at the end, what you get is you get a dual problem, which is a maximization over my Lagrange multiplier of some function of lambda. Okay, so the function also decouples a bit. So you can look at the paper if you want to know more. But this is really standard in optimization. Whenever you have like a simple primal objective and some constraints, Lagrangian will make your life easier. Okay, so this is the dual formulation, and which is used a lot in optimization. And I see some expert in the room up there, that it's very common. You start with a problem, find a dual, and hopefully the dual can be easier to tackle. So the way we're going to tackle it by simply doing like the simplest algorithm that we know about, which is accelerated SGD. Okay, no S, accelerated gradient descent. Okay, so here there is no stochasticity at the moment, and the magic here is that, and this is not apparent in those slides, is that when you do a gradient descent on that function of lambda, it turns out that it is exactly equivalent to doing one gradient step of the function that you want to optimize and one gossip step. Okay, so this is like not trivial at all. Okay, so it's hard to see at the beginning, but this is really something which makes this gradient descent step very nice, because you can do it by respecting the constraint that we have set up, which is local computations and communications only to my neighbors. And if you do that, then you can apply a result that we know about for optimization. The number of iterations will be square root. You end up with something like that, gradient steps. And since every iteration is one gradient step and one communication step, you end up with the same number of gradient steps and communication steps. Okay, so this is what you obtain by just simply finding a formulation where you can apply like a classical algorithm. The problem is that it's not optimal over there because we have this dependence on the mixing time of the graph. So now we still want to make it optimal because we want to remove the square root of gamma. And for this, we did need something more, which is accelerated gossip, which I will present now. So what is accelerated gossip? This is a very simple technique to accelerate gossip. So what is gossip? This is simply a linear iteration of that form. And whenever you have some linear system like this, okay, linear dynamical system, there are many ways to accelerate it based on the same principle. So in the context of gossip, this has been done by several people, either called Chebyshev acceleration or shift register gossip. And the principle is very nice and simple. So we're going to take linear combinations of my iterates. Okay, so I'm going to let this go through. Okay, and I want to combine my iterates like this. Okay, I'm going to average over the past iterates, which is very common in optimization. But since every theta k is a power of the matrix W times the first vector, what I get here, I get a polynomial in the matrix. Okay, so I take a polynomial in the matrix like that. So now, whenever I do averaging of iterates, it's like choosing some polynomial and applying it to my initial vector. So now you may ask, what is the best polynomial? And this is what those people have answered, and they have answered it in the context of gossip. But this is a well-known technique in linear algebra. And the best you can do is a so-called Chebyshev polynomial. I won't give any details here. And so the bonus point is that the best you can do to minimize the error, so you want to find the best so that eta t is as close to the average as possible, is as a name, it's called Chebyshev. And even better, you can compute it online. Okay, so this means that you can go from t to t+1 without having to recompute everything. You can update it online. So this is a well-known like Chebyshev recursion. And at the end, when you apply it to gossip, this looks like something of that form. There should be a t-2 over there, sorry. So you do regular gossip, but you add a bit of momentum. You get some memory of the past iterations. So this is very similar to acceleration for the convex case. And like acceleration, this will be replacing the condition number, which is here, gamma -1, by its square root. Okay, so here this is essentially the exact same technique of acceleration, but done for the gossip step. So now, let's go back to my grid. And look, so we start. Where is it? Up. Oh, some people have tested the video before. This is what's happening. Okay, so you start. So this is the start where you have your data. So positive number on the upper left, negative number on the lower right, and you launch. And the idea is that on the right it goes much faster. Okay. So here you can see that the spreading of information is much faster. And after, so here 100 iterations, you essentially have converged, whereas the other one is still like struggling. Okay, so it's just to, and in fact, this plot to me is, I had never did that before like 2 days ago, okay? And to me, it's really the reason why you need acceleration for the gossip step. If you don't do acceleration, information is being spread far too slowly. All right. All right, so now we can combine acceleration and this. So by just replacing a gossip step by an accelerated gossip step, Yep. Now we get the best complexity. Okay, so this is like, I'm not giving details, but by just doing acceleration at all levels, acceleration for gradient descent, like Nestor acceleration, and acceleration for gossiping, you get the best performance you could get for this class of problem. Again, optimal means optimal for a particular model of computation. Okay, so in many cases, that model is too big, and you know more about your problem, so you could do better. And in fact, we can do better, and I will give one example now, which is machine learning. Okay, so for the moment, for the last like 20 minutes, I've tried to look at the finite sum, but I said nothing about the finite sum. I say, yeah, it comes from some data, okay, but I was accessing the full gradient of fi. I was never looking at the case which I care about, which is machine learning, where every function is also a finite sum. Okay, so at the end, when you do like at least for machine learning, distributed optimization, you have a finite sum of finite sum, and I was just studying the first level. Fi was generic, and I didn't know anything about Fi. So now let's try to look, what if we do machine learning, because it's a nice thing to do, okay? And let's try to compare, and this is, to me, the most important slide of the talk. Let's try to compare the best you can do on a single machine. So let's say I'm going to take all of my data and drag it back to a single machine and just apply the best thing that I know of, like variance-reduced LGD with acceleration. This is the time it will take, okay? So since I have like n nodes with n data points each, overall I have nm observations, I put them in a single machine, I run my algorithm, single machine, okay, 2 lines of code, 0 communication, easy, and this is the rate that I know, okay? So this is like the result of an accelerated variance-reduced optimization, okay? And now, let's do my other thing, which is supposed to be optimal for distributed optimization, and it's called MSDA, so this is what I presented earlier on. And what I've shown is that you need some communication steps, fine, but you also need some gradient steps. And because the gradient steps require to compute gradients of the function, so if you assume like that all functions fi corresponds to the same number of data points, then you get number of gradient steps times m, number of observations. So now what you can see is that if okay, so it's supposed to be, yeah, so if you go from 1 to 2 machines, okay, so now let's say we apply MSDA to a single machine, then, so n equals 1, so we, compared to this, we have a factor of root m different, okay? So here, in a sense, when you go to 1 to 2 machines, you're much slower. And this is very common to many frameworks when you do distributed optimization, is that when you go from 1 to 2 machines, you're not allowed to use the fastest algorithms on a single machine, and you lose a lot. And here, if we apply MSDA to machine learning, we do lose a lot, okay? So this is a very common issue when you do distributed computing, is that you're supposed to compare yourself to the best you can do on a single machine, okay? And if we do that, we lose a lot. And I will show examples later on in the talk where I can't even run it on a cluster. Why? Because it is not adapted to having large data sets. It is optimal for its own class of problems. So problems which are finite sum, for which I don't know that the finite sums are themselves finite sum, but it's not optimal for machine learning. All right, so at the end, it's optimal, what I've presented so far, but not adapted to machine learning. And there's a huge slowdown when you go from 1 to 2 machines. Of course, if you go, let's say you're Google or Facebook, you go from 1 to 1 million machines, of course you're going to gain, okay? But I think let's be smart and try to design the good algorithms. Then it's also only synchronous, okay? So I'm not going to talk too much about it, but we can make it asynchronous, so communications can be known like at any given time. All right, so this is the work that I've done with Adrien Hendricks and Laurent Massoulier, which is going to appear in EURIPS this year. And this is, the goal was to tackle the case when you have a finite sum. Okay? So the first goal number 1, we really want to make this work for machine learning. Goal number 2, we want to make sure that if you reduce to a single machine, you're still doing very well. Okay? And goal number 3, which I'm not going to talk about, is to allow for partial asynchrony. So you want really not all nodes to communicate at the same time. You want like nodes to wake up whenever they want. Okay, total freedom, no boss, no constraints, and this is a pure asynchrony. So we only achieve like some partial versions. So if you want to know more, you can come to see me after the talk. So what we end up having, and I will present details in the next slides, is essentially what we hoped for. So communication steps, we do the same as for the full gradient descent. But at the end, in number of gradient steps, we improve significantly over what we had before. And we essentially take what we had for a single machine and replace and reduce the number by the number of observations per node. So this is what you want when you distribute data. You want to at the end get a result where your complexity is the same as if you had a single machine with 1 over m less m times less data. And this is what we obtain over there. So the way it works, one slide, okay, it's very simple. At least in the principle, the details are a bit complicated, but let me just give you the principle because this is really, I think, a very nice trick that Adrien has found. So I'm going to focus on the finite sum of finite sums. So to make things simple, I'm going to assume that I have some regularizer, square L2 regularizer. So this is a finite sum of finite sums, okay? And this is my original problem, okay? So I have 3 nodes over there, okay, and each of them is a finite sum. So now, the way we're going to do it is by creating a new graph, okay, and by assigning functions to that graph. And the graph he has found is you keep the 3 nodes over there, you put the regularizers inside those 3 nodes, those functions, and then you create a fake graph where you connect every node there by all copies of all the functions Fij which you have in your finite sum. So at the end, you have a very big graph because here you have like n nodes, n being the number of machines, and here you have m functions. M is the number of data points per functions. Okay, it's a huge graph, and if we apply here, so each node has a copy of its own parameter. Okay, because so every node has a single copy. We're going to add, similarly to before, Lagrange multipliers. Okay, a bunch of them. And now, if you apply to that graph dual, randomized, accelerated coordinate descent, okay, so you add up all the Base and Wilsons of convex optimization. So dual because I'm going to take the dual, coordinate descent because I'm going to only optimize over some parameters, and this has the effect of being local. When I select an edge, so here every dual parameter is an edge. Okay, so I select an edge. It's like being like asynchronous. So randomized because I'm going to access randomly to my gradient, and accelerated because I want to get full acceleration. And if you do this, a nice other aspect is decoupling of the number of data steps and gossip steps. So what I had before was, it was nice, but there was the issue of every time I gossip, I have to compute gradients and so on. So here I can adjust it. And now the way it works, and I'm almost done. Okay. The way it works, okay, here on the simple data set, okay, so 10,000 observations and in small dimensions. This is just to be able to compare to all algorithms. Okay, so this is on the left on a small network, okay, 4 nodes, and here on a bigger network, 100 nodes. So here on the left, so all of those are methods not based on finite sum. Okay, so not adapted to finite sum within every node, so they're all not very good. And what we have here is 2 nodes. So the green is us, ADFS. No, the blue is us at the ADFS, and the green is point saga, which is what you do when you put all data on the same machine. Okay, you say, okay, I have 4 machines, but I don't care. I put on a single machine, and I do optimization. Here you can see when you have a small graph like this, putting everything on a single machine is almost as good as doing the best we can do on multiple machines. Okay, so saying that if you have a small number of machines, maybe all the overheads which are associated with doing distributed optimization are not worth the effort. So this is so we do similarly, but as soon as you go to 100 machines, we're supposed to be between root n and n times faster. And this is what's happening over there. So the green thing starts to be very slow, whereas the ADFS still optimizes very well. Okay? So here, the other techniques, so MSDA is a batch algorithm. So it goes down like a line in a semi-log plot, but the slope is very slow. So this is for like small data like that. And we have bigger data to show. And this is, I forgot which data set it is, but it's in bigger dimensions over there. This is like with 100,000 observations. So here we could run only the method which are adapted to finite sums. So DSBA, I forgot what it is, but this is like other people. And at the end, we can achieve so both linear convergence rate, so it's a line in a semi-log plot, and it does converge reasonably well. So this is on an actual cluster, okay, the cluster at Inria. And if you want to know more, this is going to be updated very soon on the web. Well, so to conclude, I presented like recent work on distributed, decentralized machine learning. And the core idea is really that you should distribute the fast single machine algorithm. So if you go from 1 to 2 machines and you go slower, it's really not very good. Okay? And we have tried to do this. So if you have n machines and m observations per machines, what we were able to do is to go from single machine to multiple machine and essentially get linear speedups for the well-conditioned problems. So if kappa is small, then you go, you get from nm to m and you get some linear speedups. So extensions, so clearly the elephant in the room, non-convex problems, okay? So for the moment we can't do it. Why can't we do it? Because our algorithms rely on convex duality. So we can't even run them on non-convex problems, but Adrien is making some progress to make things like primal only, okay, with only gradients. Then we'd like to show, is this the best you can do? Okay? And in fact, now we have a result showing that this is the best you can do if you have finite sums within your finite sums. And he has gone to Redmond in Microsoft to do some experiments on a real cloud with Microsoft, and hopefully next year or 2 years in Saclay I can come back to present those results. Okay, thank you for your attention.
Thank you for this interesting presentation. Is there questions about distributed machine learning?
Hello, thank you for a question. Sorry, could you go back 3 slides before where you compare Point Saga with ADFS? Yep. Sorry, just I don't get why the P Saga is not the same result on both picture as it's running on a single machine in both cases.
It's a good question, I think, because we get more observations. So this is, so here, M is number of observations per node. So if you have more nodes, you have more data.
Oh, okay.
Okay. Well, okay.
Thank you.
Hi, nice talk. I was wondering in the non-convex case, so where the fastest single machine algorithm are slower than maybe some of the cases that you investigate here, how important is it to accelerate the propagation, sort of the gossip scheme? Is it as important?
I think we are now considering, so this is the analysis for the pure finite sum. Okay, so we can do the parallel analysis for pure AGD, okay, where all the linear rates are becoming like 1 over n type of rates, and this is in progress. But I do believe that gossiping is important because if you look to me, okay, I was really amazed like by that picture, is that spreading, and I think many papers they take graphs which have a good condition number, okay, a good mixing time. So clearly, if you're lucky enough to have a good mixing time because your engineers have designed a good network, fine. Then acceleration is worthless. But if you have like a grid, which is in a sense the worst possible graph for mixing time, then you have to accelerate, otherwise it takes forever to gossip. Okay, so this is, I do believe that acceleration is really important to avoid like waiting forever. Okay, and so this is, yeah. So I do believe that we're going to need it at some point. As a hint, so last year at NeurIPS we had a paper on the non-smooth case, which is closer to stochastic AGD, and we also did acceleration.
Thank you for the nice talk. I have a question. You mentioned the case when the graph can change over time. In this special case, for example, you will have to compute a spanning tree at each time for the centralized version. Do you think that the decentralized would be a better option in this case, or not necessarily?
This is what people are selling. I have no clue in practice. Okay, so I think if you let's say if you take the robustness to a missing node, So as long as your missing nodes do not disconnect the graph in two pieces, it should be fine. Okay? So if you start to change too many things, it's not going to work very well. So we have tried to add some robustness. So if your network is changing slowly enough, then things are fine. So it's very similar to if your data are not ID, but they follow a Markov chain which is mixing very quickly, then things are fine. So you could add some robustness to moving networks, but we have not done it at the moment. But at the moment, we cannot do it because so our algorithm rely on dual functions, on dual variables. And those dual variables are attached to the graph. So at the moment, we cannot. This is why having primal-only algorithms, okay? So there are a bunch of those, okay? So here, on this, there's a bunch of primal-only algorithms, and I forgot which ones are which, but they do get primal-only. So those who benefit from the will be robust to changing networks, but they don't use acceleration. So to me, it's an open problem to bridge the gap between really robust algorithms to changing networks and acceleration.
Yes, I was just wondering, you didn't talk about step sizes and gradient method, which is usually a big issue, isn't it the
Very
case?
good question. So let me go back there. So sometimes people mock me because I focus too much on the step size. Okay. Yeah. So if you go back, indeed, if you go to batch gradient descent, the step size is easy. You can do line search or a constant. It's considered as being a solved problem. For IGD, in the pure streaming setting or even that setup, it's always a problem, okay, to find a good step size. But the beauty of those like accelerated gradient algorithms, and this was written on the slide, is that the choice of the step size is being given to you. There is no step size. And to me, this is, in fact, one of the key benefits of those fast gradient techniques is that they are robust. You take a problem, you run it, it works. Okay? For example, I think in scikit-learn now for L1 regularized logistic regression, it's a saga which is implemented. You launch it, there is no worry about, oh, will it converge or not? Okay, you have a step size, which is working well in practice, and for which you have a bound. Okay, so this is really what we aim for, having algorithms for which you have guarantees, but still work in practice. So in many papers, typically, you have a step size to get the bound, and a different step size to do experiments. Okay, we're not doing this. The step size is being given by the math, and we use it in experiments. So we don't manipulate step sizes to get better behavior in practice. And this is really a key benefit of those techniques, because if you do AGD, you really have to tweak the step size quite a bit.
We have time for one question. So I have one question. How far the methods that the algorithms that you are proposing can apply to machine learning problems that are multitask, multi-labels, or
No, very good question. So I think if you go back to my finite sum, so here we took we studied one model which is common to everybody. Clearly, this could be what you want, but you may want, when you do the dual problem here, instead of having like the same model for everybody, you may want the models to be close enough. Okay, so this is classical multitask learning. So we call it federated learning, but it's multitask learning, okay, from 10 years ago. And this clearly, you can adapt it. And essentially, this corresponds to not having a Lagrange multiplier which is penalized a bit. So you can include very easily like the multitask aspect if you want to penalize the deviation between the models from different nodes. Because really, it's a big. It's interesting. The problem is that then you have to quantify the amount of sharing which you want to do, and this is like complex to get. Because in many instances, So I've done multitask learning like 10 years ago, and what you often see in papers is that to get the benefit of multitasking, it's really from one really small regime of number of data points. If you have lots of data, you don't care about sharing. If you have really no data, nothing works anyway. So between like no data, almost no data, and a lot of data, there is a regime where multitask is really important. And I don't know if we are in that regime for practical problems at the moment.
Okay. So thanks again the speaker.